You'll recall that before we looked at the derivative of f at a, and we had two definitions for it. One of them was a limit as h approached 0 of f of a plus h minus f of a divided by h. And the other was the limit as x approaches a of f of x minus f of a over x minus a. These are both the derivative at a point. And each of these will give a value, a number for a derivative. Here we're going to look at a new definition. It looks a lot like the first one. And it's the derivative of f as a function of x. And it's the first difference quotient, except we have x's instead of a's, right? So f prime of x is the limit as h approaches 0 of f of x plus h minus f of x over h. The difference here is the first definitions, the first two definitions we just looked at are the derivative of f at a. Let me circle what I meant to circle here. And the new one is the derivative as a function of x. Right, so these first two we're going to say are from before, and the result is a number, which can be considered the slope of a tangent line. Here the result is a function of x. Now, the function itself can give you a slope for any value you place in place of x, but this thing is a function. And we're going to see how they differ as things unfold. Let's look at an example. Find the derivative of a function f of x equals the square root of x minus 6 using the definition of derivative. So we're going to use this difference quotient with the x plus h business. State the domain of the function and the domain of its derivative. Let's just do all this in order. F prime of x is equal to the limit as h approaches 0 of the square root of x plus h minus 6 minus the square root of x minus 6 all divided by h. I'd like for you to go ahead and do this and come back when you're done. Hopefully you got that f prime of x is equal to 1 over 2 times the square root of x minus 6. As you can see, it's a function of x. For any allowable input value that I put in place of x, this will give me the slope of a tangent line. But as it sits right now, it's just a function of x, and it's the derivative of f. Now, we were asked to find some domains, right? So the domain of f, well, f is equal to the square root of x minus 6. So the domain of f is 6 to infinity, including 6, right? The domain of f prime, because the square root of x minus 6 is in a denominator, is going to be the interval from 6 to infinity, not including 6. So sometimes the domain of a derivative can be different than the domain of the original function. Here's the thing. The domain of the derivative will never be bigger than the domain of the original function. It can be smaller, but it'll never be bigger. Now let's look at some notation. F prime of x is also written as d dx. It looks like a fraction, but we do not use the word over. D dx of f of x, or in other words, the derivative with respect to x of f of x. Y prime if our equation was in y and x instead of f of x. Dy dx, that is the derivative of y with respect to x. And then d sub x, you don't see that one very much, but it's valid. They all represent the derivative of f or y with respect to x. Sometimes we find a derivative like we just did, and then we evaluate it at a point because we want the value of the derivative at that point. We want a slope of a tangent line or something. So the way we can denote that is we can say f prime of 2, right, using function notation. And another way to write it would be dy dx with a vertical line and then a little x equals 2. These both mean the same thing. They say I've taken a derivative of f or y with respect to x, and then I substituted 2 in place of x to get a number. Now you can imagine we can start with a function f and then take its derivative. Since the result is a function, I can then take its derivative, right, if that limit exists and all of that. So There are things called higher order derivatives. If I've taken a derivative twice, I'm going to denote that using two apostrophes, f double prime. We don't really say f prime prime unless you're just trying to have fun. So f double prime of x is y double prime. This one's a little interesting. D dx of dy dx. So what we're saying is I'm taking a derivative with respect to x of the derivative of y with respect to x. So inside the parentheses, we're saying I've already taken a derivative. And then outside, we're saying now I'm doing it again, both with respect to x. And then that d dx dy dx can be denoted d2y dx2. We don't say over, we don't say squared. It's not squared. It's saying it's a second derivative. So d2y dx2. They all represent a second derivative. Third derivative, f triple prime. And in this notation here, it would be d3y dx3. And I just realized there's something I want to tell you. This f prime of x, actually, let me use a different color. The f prime of x and the y prime, these are both what's referred to as Newton's notation. Newton was one of the people who came up with calculus, and that's how he wrote things like this down. And then there was another guy. His name was Leibniz, Gottfried Leibniz. And the dy dx stuff, that's how Leibniz wrote stuff down. So the primes are due to Newton, and then dy dx is due to Leibniz, who was another guy who came up with calculus. So the Leibniz notation for a third derivative would be d3y dx3. We don't just put prime, 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 prime if we have like a fifth derivative. After 3, we use parentheses to denote the derivative. So f exponent looking 4, but the 4 is in parentheses of x, that would be the fourth derivative. How many derivatives can we take? As many as the function will let you. It may not be meaningful to take 20 derivatives, but maybe it is, who knows? But if we have a position function, say s of t gives a position as a function of time, then its first derivative is velocity. That would be change in position over change in time. We can think of this as maybe like meters per second or feet per second. That's velocity. The second derivative would be how velocity is changing over time. So the second derivative is acceleration. The third derivative is how acceleration is changing over time, and that's called the jerk. So for the second derivative, we can think of like the derivative with respect to time of ds dt if I'm using Leibniz notation. And in terms of units, if I want to know how the meters per second is changing over time, that becomes like meters per second squared. Those are units for acceleration. And then the jerk would be meters per second cubed. We don't see that a whole lot, but it is a thing.